Hello, I welcome you all. The problem reads that the zero point 0.8 megagrams car travels over the hill having the shape of a parabola. If the driver maintains a constant speed of 9 meters per second, determine both the resultant normal force and the resultant friction force that all the wheels of the car exert on the road at the instant it reaches point A. Neglect the size of the car. I only solved the first problem. Both problems are coming from the Engineering Mechanics and Dynamics, a 14th edition by RC Hibbeler. So I'll solve this in the next video. Okay. Right now I'm working on the first one. Alright. So let's draw the free body diagram. Again, here we have been asked to determine the um um, the resultant friction force as well as the resultant normal force at A. Okay, and we've been given the function that governs this particular here, which is a parabola. Right. So let's draw the free body diagram of what is happening. So we are going to have, so imagine there's a car here. We have a car, the same car has moved to this point. So let's redraw this car. Can we redraw it or can we snipe it and then replace it there? Can we do that? Maybe we can. Let's try that. There we go. So let's place it there. Okay, not too good. Maybe we tilt it a little bit. Maybe something like so. Let's get it. Alright. So that is the point. So this is the point here. And that's A. That's point A. So we are saying at that particular point, let's draw what is happening there. So we are going to have friction force at that point, like so. Okay, tangential at that point, and then we'll have normal force. Normal force will be coming normal like so. Let me draw it properly. Normal, something like that. Okay, right. And then we do have the weight of the car. Let's say the weight of the car is something like this. Okay. Let me maybe use black. So there we go. We have the weight of the car like this. Okay, we'll clean it up here. But this is still the weight of the car. So these are the components that we have so far. We have the weight, we have the friction force in the opposite direction of motion. So this is the weight, which is just equal to mg. This is the normal force, right? And this is the friction force. Okay, this is the resultant friction force. All right. And then we'll need to find the angle. We need to find the angle at this point. We need to find the angle. This one. We need to find this angle here. This angle here. We need to find this angle here. Let me just show this angle here. We need this for us to be able to work at the same point A. This point here, it is point A. So we have this point here, okay, which is point A. So this point here is point A. Okay, that is point A. All right. So how do we find this angle and everything else? So what we need to do is we do have the function here that we are going to use, and then we do have a coordinate. Let me show some coordinate here. We have some coordinate along this direction, which we are calling n, along this direction, right? That one is one coordinate, and then we have another one there which is another coordinate. Let's label these. So this is T tangential, this is T tangential, and this is N. Okay, and then we do have motion. So motion along this direction and along that direction, right? And the B is coming out of the screen. So this one here is M80, this one here is MAN. Okay, so I think we are done with the free body diagrams. We can now begin to work. So we need the curvature rho, we need that angle, and then later on apply the equations of equilibrium, right? So let's go ahead. So y is equal to 20 1 minus 1 minus x squared divided by 6,400. This is the function that governs the hue. Okay, it's parabolic in shape. So let's use this function to determine the curvature, the radius of curvature, as well as the angle. So we know that y prime is just going to be equal to 20 and then minus 2x divided by 6,400, and then y double prime is just equal to 20 by just a minus 2 divided by 6,400, like so. So if we worked out this just becomes 20 by 2 divided by 6,400. Alright, we'll leave it like this. So this just becomes, so that it doesn't become too small. See, just 40 or 4 divided by 640x, and then this one just becomes minus 40 over 640. Alright, but we do know that y prime itself, y prime, finding the angle, is just equal to tangent theta. Okay, and this is equal to this minus 4 over 640x. Okay, so y prime at x equal to 80, this just becomes equal to, at 80, what do we have there? That is 4 times 80. Okay, 4 times 80. So this just becomes tan theta is equal to minus 320 divided by 640. Therefore, theta is just going to be equal to tan inverse of that number minus 320 divided by 640, and this is just going to be equal to, that's minus 320 divided by 640, tan inverse of that, we have a minus 26.57 degrees. Okay, so 80 by 4, okay, minus 4 by 80 divided by 640, tan inverse of that is minus 26.57. So the minus here, this angle therefore just simply means this angle is clockwise. We can also write it like this, 57, like this, and this angle shows that it is like so. Okay, this is what it means. All right, clockwise, like that. So this is what it means. So this is the angle. We have found the angle, which is fine because we need that angle. And once we have that angle, then we can relate here, can draw down this line like so. So we know that, let me move this end somewhere else. We move it this side, we move it this side. So we know that this is also equal to theta. This angle here is theta, right? Do you agree? Of course, you are supposed to agree. Okay. So if that is theta, then we know that that line there, this one here, this like so, this angle here also will just become equal to theta, right? Because we need the component of this W, right? So we need this component along this direction like so, okay, and another component like so, okay. Like so, right? All right, so these are the two components. So we have this one, which is W cos theta, and then we have this one, which is W sine theta. So these components, we need them when we begin to apply the equations of motion. So let's now begin the work. I guess we've written a lot, we've talked a lot. So let's start with the t-axis. So I'll say summation of forces along the t. This is equal to mat. But since our at is equal to 0, this just becomes equal to 0. And this is our positive reference. So what do we have in this direction? We do have w sine theta. Okay. W sine theta minus the friction force, which is F. And this is just going to be equal to 0. And therefore our friction force just becomes equal to W sine theta, and this is just going to be equal to mg sine theta. So F will be equal to, our m here is 0.8 by 1000, so this just becomes 0.8 by 1000. This is mega is 10 to the power 6. So 0.8 by 1000 times 9.81, and then sine the angle which we just calculated, which is 26.56. Therefore F, which is the friction force, is just going to be equal to F, which is the friction force, and is going in that direction, is equal to 0.8 by 1000 times 9.81 times sine 26.557. Sorry. So this just gives us a 3510.34 newtons. So let me just rub that. Okay, so this is 7. All right. So 0.8 by 1000 times 9.81 times sine 26.57, 3510.34. So we found the friction force. So we need to move now to the next step, which is now finding the what else are we finding? Let me just work out this. I changed there like so. What else are we finding? We are supposed to find the normal force. So we are going to say summation of forces in the n direction is just going to be equal to MAN, going down being our reference positive, where AN is our centripetal acceleration, and this is just equal to that, like so. Our V is given as equal to 9 meters per second, and our rho is just equal to, we need to calculate rho here. Let's calculate rho. So we can calculate rho. By just using the equation of curvature. So rho is just equal to 1 plus y prime squared and everything to the power 3 over 2 or 1.5 and divided by y double prime. So our rho therefore will just be equal to 1 plus y prime at 80. Y prime at 80 we found is equal to minus 320 divided by 640 squared and divided by y double prime is minus 40 divided by 640, and this we always just take the modulus. Okay, and this we are multiplying by to the power, you're raising it to the power 1.5, and therefore our rho will just be equal to, let's work it out, minus 320 divided by 640 is 0.5, and then we have 1 plus 0.5 squared, and that to the power 1.5 divided by 4 over 640, right? Okay, so our radius of curvature is 223.61 meters, right? So 1 plus 0.5 squared to the power 1.5 divided by 4 divided by 640. 4 divided by 4 divided by 4 divided by 640. It's 223.61, right? So with that in mind, therefore we can say we have in that direction, we do have W cos theta minus N is going to be equal to mv squared divided by rho. Subject to the formula, N is just going to be equal to, if we took it the other side, this becomes W cos theta minus mv squared divided by rho. Therefore, our N will just be equal to M. We factor out M, we have G cos theta minus V squared divided by rho. Therefore, our N will just be equal to 800. Our G, we have 9.81 cos 26.57 plus 9 squared divided by 223.61. Right. So therefore N will just be equal to, is a minus here, sorry, this one here is a minus, there is a minus like so. Okay, so that, let's work it out. We have 9 squared divided by 223.61. okay, this is a minus plus 9.81 cos 26.57, all right, then times 800. So our N therefore just becomes 6,000. Let me get black. 6,729.29. Okay, point 37 newtons. Okay, so we have 9.81 cos 26.57 minus 9 squared divided by 223.61, then times 800. So 6729.37, that is the normal force. The normal force, resultant normal force. Okay, I think this is about it. We have found the friction force, resultant friction force, and we've also found the resultant normal force. Okay, I think this is about it, and I hope this particular video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.